conditions we can, in three various conditions we can define inertia. One is inertia of rest, other is inertia of motion, and other is inertia of direction, etc. Inertia of rest, when I discuss, it is very simple to explain you. Suppose that there is a cup of water. There is a cup of water kept on a table surface, and you see there is uh, a plane. A plain cardboard is also kept on the surface of this, and a coin is placed. So this is water essentially. That means the cup of water is covered by a lid. On the lid, a coin is kept. Okay, this coin is at rest. If at a very uh, good speed, that which is snatched with a great speed, which one? The cover is snatched with a great speed, then what will happen? The coin will fall into water. Why the coin will fall into water? We are pulling it outside with a good speed. Which one? The cardboard is, or the lid is pulled with a high speed. In that condition, you will see that the coin will not go with the lid which is pulled out, but the coin will remain at the same position itself and will fall down into water. You can also do this experiment at home, right? It means that because this coin has a tendency to remain in the same position itself. That is why it is not moving with the lid which is pulled with a speed. So this is the best example that you can practice at home, do at home, and understand what is inertia of rest. And so many other times, so best examples you can also experience. Suppose you are sitting in a bus and the bus is not started yet. All of a sudden, when the bus starts or car starts, you will see that you will go backwards. That means your back part of the body goes in the backward direction. This is when the bus or car is started, one part of the body which is in contact with the seat of the bus, that starts moving, while the other free part, half of the portion of the body, still has a tendency to be at rest. So these are all the best examples of inertia of rest, right? Another best example is that to clean a blanket, woolen clothes and all. What do? You will take a stick like this and it is beaten up. Repeatedly it's beaten up. Then what are the dust particles move away. But actually what is happening is when we are beating the blanket with the stick, that part of the blanket starts moving, right? While the dust particles has a tendency to be at the same position itself. So it gets separated. So this is also another example of what inertia of rest. Okay. Another best example, practical example that you can see is that mango. So there are so many mangoes which is hanging down in a branch, and the branches when shaken, so many mangoes will fall down. Why? When we are shaking the branch of the tree, the branch of the tree starts moving, while the mango fruits are still has a tendency to be in the same position itself at rest. So these are the best examples of inertia of rest. Another is inertia of motion. Inertia of motion is very interesting to see. Suppose you are sitting in a bus and the bus moving and moving. All at a sudden, when it stops, what happens? Your body, the upper part, the free part of the body starts move in the forward direction. Why that happens? Because when the bus stops, one part of your body which is in contact with the bus or the seat of the bus gets stopped, while the other part, free part, is still has a tendency to move with the same speed the bus was moving with. So this is the best example of this also, right? Another best example you can see is that we are just go on shaking a mango tree. The mango tree means a branch of a mango tree. Once in the first time, some fruits will fall down. After that, the fruits will not fall down, right? Once when you stop it, now the fruits will starts again falling down. Why that? Because the mango, when the branch was going on continuously shaken, the mangoes were also in a state of motion. All at a sudden, when it stops shaking, what happens? The tree branch comes to be stopped, comes to be still, but the mangoes are in a state of motion only. That is why this imbalance will make the mangoes will fall down continuously. When the shaking process stops. Right? These are the several examples that you can see. Other one is called the inertia of direction. Inertia of direction is also very important because a body which is moving in a certain direction, that has a tendency to move the same direction only. If all of a sudden a change takes place, imbalance will take place. For example, you are sitting in a bus and the bus is moving in a straight road. All of a sudden, a turn comes. When the bus turns, you will see one side of your body will go outward. That means in an outward direction of the circular path, away from the circular path, it has a tendency to move. Why that? The bus moved in another direction, but your body wants to move in the same direction only. That is why you are getting pushed into the that side of the bus. Your body go and hits with that side of the bus. That means it has a tendency to move outward from the circular path. So this is the direction, right? So inertia has three conditions: inertia of rest, inertia of motion, and inertia of direction. Next is equilibrium of concurrent forces. Concurrent forces mean forces which are acting at the same point are called concurrent forces or concurrent vectors, because force is also a vector. So equilibrium of concurrent forces, I am going to talk something about. Equilibrium, third part is equilibrium. Equilibrium of concurrent forces. Concurrent forces means the forces which are acting at a particular point, or forces which are simultaneously or at the same time many forces are acting on a body. Yes. Suppose this is a point, and here so many forces are acting. One force is like this. This is F1 force is acting. This is F2 force is acting. Here F3 force is acting. This is the point O. Right? This body, and the body remains at the same position itself. It is not getting accelerated. That means the resultant displacement of the body is equal to zero. That means this acceleration is equal to it is not getting accelerated. It is the body is not getting accelerated means the force acting on the body becomes equal to zero. Then we can say that these concurrent forces are in equilibrium. That we can explain. Suppose these are two forces, and these two forces can be adjusted by the two sides of the parallelogram. Then then the diagonal of the parallelogram will be the resultant of the forces. Suppose this is O, this is A, this is B, and this is C, and this is C dash, I can say. Right? The resultant of these two forces is this. What is F? F is F1 square plus F2 square plus 2 F1 F2 cos theta. What is theta? Theta is the angle between these two. We can calculate the value of F. And now, if this point is not moving either upward direction or downward direction, it means that this vector F is equal in magnitude but opposite in direction of F3. So when two forces are acting at a point and these two are in equal magnitude but are acting in the opposite directions, they are called balanced forces. If the force is balanced and it is acting on a particular body, the body will remain at the same position itself. It does not get accelerated. That's the situation, right? So this is called balanced force and unbalanced force. If the force is unbalanced, suppose this F, that means vector OC is greater than vector OC dash, then the body has a tendency to move along this direction. Or vector OC dash is greater than vector OC, then the body will move in the other direction of F3. These are called unbalanced forces. In that condition, there is a resultant force. Just like two groups are pulling a rope standing at two sides, right? One is pulling on that side, other pulling in this side. If both are of the same ability, same force both are applying, then the limit mark point will remain at the same position. So that means balance. If one of the team which is stronger than the other, then that side, the limit point, the mark point, middle point, that will move towards that. Okay? In that case, we'll say that the force gets an unbalanced, imbalanced force. Then there is a resultant displacement that takes place on the body, or the body gets accelerated in the direction of the stronger force. Other cases, we can say that the force is balanced. In this case, suppose that this point O is not moving either towards this direction nor moving towards the other direction. Then we can say that the forces are balanced. Then what we can say? We can say that now vector OC, sorry, vector OC dash is equal to minus vector OC we can write. Right? Okay. What is F1? F is equal to F of vector F1 plus vector F2. That is vector OC dash is equal to minus of vector F1 plus F2. F1 plus F2. Right? So resultant vector, if this is P and this is Q and this is R, resultant vector R is equal to vector R is equal to vector P plus vector. We have studied in vectors. Vectors I have taught you, then you might have seen that vector R is equal to vector P plus vector, right? And the magnitude of the resultant vector, modulus vector R is equal, modulus vector P plus vector Q is equal to square root of P square plus Q square plus 2PQ cos theta. What is theta? Theta is the angle between the two vectors. Very clear? This is the vector OC is equal. What is vector OC? Vector OC equal to F3. That is, vector F3 is equal to minus of vector F1 plus F2. Right? That is, so we can write all these things are taken this side, then you will get, that is vector F1 plus vector F2 plus vector F3 is equal to 0. That means when two or more forces are acting on a body and the body is in equilibrium, then the sum of all the forces is equal to 0. This is what is called equilibrium of forces. When several forces are acting on a body and the body is not getting accelerated, the resultant force acting on the body is equal to 0. Then we can say that these forces are in equilibrium. Two forces also can be in equilibrium. So two forces are acting on a body and the body is not moving towards this side or towards this side. So it is still. Suppose I am standing here like this at the camera, you can see my one hand is pulled by one person, other hand is pulled by another person, but I am not moving to either sides. Then I can say that the two forces are in equilibrium. That means balanced forces. In balanced forces, there is no resultant force. The resultant force is equal to 0. That means magnitude of one force plus magnitude of the other force is equal to, the one force plus the sum of one force plus the other force is equal to 0. This is vector addition. It is not a scalar addition, right? So remember that. So this is about one thing. Now I am going to tell you about another theory, that is what is called the three forces when only three forces. This means any number of forces can act. But luckily we got only three forces here also came up. That's all. But only for three forces are acting on a body, then there is another law, that is what is called Lami's theorem is applied. Suppose in this case also I am telling you this one, all these things I am removing. Yes, this is naturally okay. This is vector F1, this is vector F2, and this is vector F3. F1, just opposite to F1, between F2 and F3, suppose the angle is alpha. Angle is alpha, right? Okay. Again, F2, leaving F2, the angle between other two is equal to beta, right? And leaving F3, the angle between the other two is equal to gamma. When three forces are acting in a body and the body is in equilibrium, what is in equilibrium means O is the body and where three forces are acting, one force is F1, other force is F2, and other force is F3. Angle between F2 and F3, that is opposite to F1. Opposite to F1, the angle between other two forces is equal. Leaving F1, the angle between other two forces is equal to alpha. Leaving F2, the angle between other two forces is equal to beta. Leaving F3, the angle between other two forces is equal to gamma. In this case, we can write what is F1 divided by sine alpha. S1 by sine alpha is equal to F2 divided by sine beta. sine beta is equal to F3 divided by sine